data, both structured and unstructured, there's going to be one key information or piece of knowledge. If present, we will use type A of machine learning, otherwise type B. And that key piece of information is the label information. Annotation. So this is an image of apple, that is an image of orange. If the images are labeled, we know the content or type of the image or the tweet or the review, customer review, or whatever the information we have in available. If it is labeled, then we are going to use those labels to train our algorithms. Those labels are going to supervise algorithms how to learn and what to learn. That's why when we have labels in the data, we apply algorithms that are called supervised machine learning algorithms. If we don't have labels in data, we are going to apply algorithms that are called unsupervised learning algorithms. We will start with supervised learning in this course, and we will also cover unsupervised learning methods, and then a hybrid of both. In the supervised learning methods, there are two main problems that we are going to deal with in this course. If the labels have discrete values, 0, 1, male, female, pass, fail, or some discrete values, more than 2 possibly, then we are going to do classification algorithms that learn to classify information into class A, B, C, male, female, pass, fail, 0, 1, whatever. If the labels are continuous information, continuous variable, or a number that has a range, for example, age, price, or earthquake magnitude, or whatever, if it is a number, we are going to do regression. Both regression and classification are going to be supervised learning, machine learning. Supervised, unsupervised, based on the availability of labels. Classification and regression based on the type of the label. If the label is categorical, we are doing classification. If the label is numeric and continuous variable, then regression. We are going to start with very simple machine learning technique that is used for, first, we will learn how to use it for classification, and then it can also be used for regression. But you may have sensed we are starting with supervised learning methods. In this particular technique is decision trees. We are going to learn what are decision trees in the first module and how do we create algorithms that learn decision trees from data. So the task of decision tree learning is basically to, given a collection of examples, let's call them X, there is a function fx. When we input those X to that function, we get a mapping. That function maps X to the label of X. There could be many possible functions. We refer to them as hypotheses as well. And possibly out of many hypotheses, if we restrict our type of hypothesis to decision tree, we are going to find out the best decision tree that can provide this function, hypothesis. So input to a decision tree is an object or situation that is described by a set of attributes. So when I mention attributes, that means we are talking about a structured data where we have columns and rows. Each column is an attribute. So there will be n attributes, we prepare them and do something to make them learnable put them in the format that is learnable, and they become features. So attributes of data, we transform them into features. And once that those features go into decision tree outputs a decision whether it belongs to class A or B. By it, I mean the X, the set of features. In case of decision trees, we are going to first focus on the labels that are discrete, but they can be continuous as well. When we conclude our discussion, we will know how the continuous variables can also be used in decision tree, and decision trees can do regression for us as well. But to start with, we are going to do a decision tree with Boolean classification problem, where the output or the label of the examples or objects are binary, 0, 1, positive, negative, male, female, etc. In the decision tree, we have nodes of two kinds, decision node and leaf node. In the decision nodes are the intermediate nodes in the tree that take us to the leaf of the tree. And each path or branch in the tree passes through certain decision nodes. A decision node will split our data into two or more branches. For example, we can take a decision tree as an inductive learning where we have examples and we want to find out the function, the rule. So input instance space X, we have these attributes, food, chat, fast, price, bar, and the amount of tip is the label. So big tip, yes, yes, no, yes. These are the labels for each example. Each example has 5 attributes. So the target function will map these values of the attributes, given the values of these attributes, to yes or no. There could be many possible functions. We refer to them as hypothesis space. But given the limited amount of examples, we are going to call those examples as training data to train an algorithm. Here we are talking about decision tree, using those examples and try to learn the best possible decision tree to map the values of these attributes to the binary outcome variable, big tip. So in here, if we use only 3 of those attributes, F, S, P are the shorthand for the attribute names. So the feature vector X1, the vector sign here, looks like the values for F is in the first one, G, for S, Y, for P, the value is A. When we input this feature vector to the function that we are trying to learn, the output should be either 1 or 0. Given the examples that we saw on the previous slide, if we put those examples through this decision tree, the food, speed of the service, and the price, then all of these examples get correctly classified to 1 or 0. The tree we are going to refer to as consistent. It's consistent with the example data. So in short, decision tree is going to represent a function that takes as input a vector X composed of the values of the attributes in the data and returns a decision Y. If Y can take only 2 values, we will say it's a binary classification or Boolean classification problem. Here, I'm going to throw in a few new words that we are going to use liberally in the following discussions. So the X we are going to refer to as independent variables, and the Y will be referred to as dependent variable. The labels are synonymous to dependent variable, attributes, set of attributes, independent variable. So decision tree will reach to a binary decision by performing a sequence of tests, and each decision will pass through certain paths in the given decision tree. And when we reach to the leaf node will contain the decision. Each leaf node will either be 1 or 0. The strength of this kind of representation of hypothesis is that It's not a black box. We can look at it and see it's consistent with our understanding of the problem. We can look at it as how-to manuals. So, given example data, how can we learn that there could be many possible decision trees? How can we learn the best one? For example, we will look at use this example in this module where we are looking at a binary classification problem determined by these 10 attributes, where we have alternate restaurant, bar, Friday, Saturday, hungry, patrons, price, raining, reservation type, weight estimate. These attributes are given, and we want to estimate whether, given the value of each attribute, the person waiting in line outside the restaurant will keep waiting or move on to the next restaurant. So the dependent variable here is will wait, which is a binary variable. Independent variables are these 10. Notice we don't have restaurant name in the independent variables. There could be many reasons. If we know the restaurant name, well, sometimes restaurant name determines whether people will stay or move on. If it's a so-so restaurant, people will just move on. But if it is someplace exotic, people would try to wait. So given the restaurant name will have some implications on learning problem. We are going to notice, take a note here that restaurant name is missing, and we will find out why an attribute kind of restaurant name is good or not good for learning problems. First hint is that if we include restaurant name in learning problem, it won't generalize well. We want to make a decision tree that works across the board for all possible situations in all cities, in all states. In that case, if we want to really make the general tree applicable to every situation, then putting restaurant name as the attribute will make the decision tree maybe shorter, but naive, not generalizable. The example data looks like this. So we have 12 examples. The target variable is will wait, and true is represented by green dot, and false is represented by. The thing is that XOR and OR are not the real problems that we are going to try to learn from the data. They are just examples of truth tables that we can look at to see how decision tree can be represented if everything is binary. In reality, we don't have binary. We have multiple values in each attribute. But to keep things the simplest way, let's assume attributes are binary, dependent variable is binary, and we want to learn, let's say, for 10 attributes, there will be 2 raised to power 10 rows required to represent the complete truth table, and 2 raised to power 10 row examples will be required to create that mapping between dependent variable and 10 independent variables, which is too much to ask. We never have that luxury. So look at these. If we have 10 variables and output is binary, this many rows and this many examples, we need to construct the complete truth table. And that, number one, we don't have that much data, never have that much data. We have only example or sample data. It's okay, having truth tables and everything is okay. But even for 6 attributes, we are looking at this many possible trees to solve an arbitrary problem, which is, I mean, if we need to go through this many trees and check which one works best, it's going to be a serious bottleneck, right? We don't have only 6 attributes sometimes. Mostly we are working with hundreds of thousands of attributes.